This recording is a pre-session for the Accessibility Summer Camp 2023. The title is AR for Learning and Accessibility, Insights from a Systematic Review of the Literature and an Environmental Scan with an Early AR Accessibility Checklist. This is by Shalin Hai-Ju at Kansas State University. This next slide shows a visual by Deep Dream Generator. It shows 3 red foxes in front of a green forest. The visual is a pop-up image from either a print or electronic book, which is one application of augmented reality. The next visual is also by Deep Dream, and it shows a biology lab that is a virtual lab. The next visual, also by Deep Dream Generator, shows the design of a living room with a digital image and a very fashionable light in the corner. So what is this presentation about? The presenter conducted a systematic review of the academic literature recently. She also conducted an environmental scan to best see how to set up an augmented reality shop at an institution of higher education. The ambition was not only to better understand the technologies, how to follow accessibility guidelines, how to be legal, but also to examine potential positive and negative effects of AR on teaching and learning. So some insights about the scholarship of teaching and learning with this technology. The research did not go past the review stage because of a lack of funding, but there were some insights about accessibility in AR. So on the one hand, AR is seen by some as positive for alternate needs of learners because it's a different modality. It's a different channel that might help with perception and cognition. Others, however, find that there may be challenges with excessive motion, busyness, shapes, and colors. There are some inherent challenges with using AR in teaching and learning based on a few general categories, which I will elaborate on later in the slideshow. So these include visual presentation and communications, insufficient information, such as in labeling, physical challenges of the AR space, unclear navigability, triggering effects, and cybersickness. So this does provide an overview and some early thoughts in the space. This next image shows falling gummy candy evoked as three-dimensional, chewy, yummy looking candies that are falling. So it evokes both 3D and 4D. This was created using the Crayon Generative Art Making AI. This next visual shows a clock that was created using Deep Dream Generator. There is a sense of 3D to it, as well as a sense of it being exploded. Section break. What is augmented reality? Thomas Kodal of the Boeing Company cited the first use of augmented reality in the record back in 1990 in industrial manufacturing. AR was used to impose information on the visual field to make it easier for workers to lay aircraft cables. There is a cited source for this, and all cited sources in the slideshow have references in the references list at the end. R.T. Azuma in 1997 first defined AR as a system that requires three components. One, it has to combine the physical real and the virtual. Two, it has to be interactive in real time. And three, it has to include the third dimension. So the x-axis, the y-axis, and the z-axis. So showing volume to emulate the world with more depth. AR does not restrict the technologies used, and various technologies are used for augmentation. These include projections, lighting, head-mounted displays, mobile apps, speakers, and others used in various combinations. There are strengths and weaknesses to all the devices, the methods, the technologies. In general, there are two general types of AR. They are considered marker-based or markerless-based, and in many cases, both coexist in the same app. Marker-based AR requires the use of a camera to acquire particular visual codes or image anchors to trigger the AR to display, to play, or to spawn. QR codes are a common example. Markerless AR spawns without visual triggers, but perhaps with users being detected in a locality through proximity triggers. There are other conditionals that may be set up to act as triggers. Section break. Augmented reality for teaching and learning. There have been various practical documented uses of AR. For example, there has been exploratory art spaces, museum displays, virtual laboratories, interactive gaming, simulations, design labs, design studios, learning modules, campus tours, electronic publications, imaginary immersive worlds, trainings, practices, sales displays, and many others. About AR for learning, AR enables experiential learning that combines the real and the virtual. This is considered immersive embodied learning. Disembodied learning is when generally only the mind is engaged, such as in reading a book or distance learning in some cases. The experience in AR is visual, including 2D, 3D, and 4D. 4D refers to motion or changes over time. Objects may be textually or symbolically labeled in AR. There may be sound, such as a background soundtrack or ambient sound. There may be event-based sound. There may be character-based sound, and so on. The experience may be interactive, such as with humans interacting with physical tactual objects like tangibles, humans interacting with digital objects, and other combinations. Collision detection is a capability for some virtual AR that helps simulate the physics of the real world, where two physical objects cannot inhabit the same physical space at the same time. The collision detection enables virtual objects to behave a little more like real physical objects based on how they behave when they run into each other. The AR experience may be social and collaborative, with people physically present or virtually telepresent, or different combinations of human interactivity with some physically present and others remoting in. The AR experiences may be held indoors or outdoors or a mix of indoors outdoors. One term used for AR spaces is, quote, spatial augmented environment, and there is a citation. The external AR experiences may be in the daytime or at the nighttime. More sophisticated systems enable adaptive contrast and lighting given light conditions. The AR experiences may be location-based, locative, in a geographical sense. Some are world-scale experiences, or they could be more local, where there might be an AR walk sequence. The AR experiences may also be non-location based. For example, there may be devices that can play various AR spawns anytime, anywhere in a ubiquitous way. AR experiences may be delivered remotely, virtually, for online learning. The designed AR can be exploratory. So people can go into a space and search for various AR visualizations. Or the AR experience may be guided, such as having individuals or small groups move from station to station. AR may be experienced individually or in small groups. The AR experience may be dynamic and ever-changing. For example, data may be streamed to change the scene or parameters of the scene. Human biometrics have also been used as feeder data to various AR experiences. This next slide shows a projector that was created in the Deep Dream generator. It is an ornate, intricate image with quilling effects. Some AR systems are fully built out for teaching and learning in a physical space. Such systems enable instructors to have administrator level access to change up the AR for the learning and to monitor the locations and behaviors of each of the learners. Some AR systems also enable data collection to understand the dynamics of the teaching and learning. Some AR systems are desktop ones, such as those for e-publications, e-books, and print books. Others are mass scale, such as projected displays painted on the sides of skyscrapers. And others are larger still, with global scale ARs designed around particular themes and/or knowledge. These depend on GPS coordinates or other ways of indicating location. Section break. Some learning concepts apply to AR. So AR can be applied to formal, accredited learning from preschool to postgraduate school, postgraduate studies, to non-formal learning, so non-accredited courses and trainings, modules, or to informal learning, so incidental learning from lived experiences. There are various learning theories that can be applied to augmented reality. I have selected some that are very practical to me and make sense to me in the context. Bloom's taxonomy of learning objectives, particularly the updated one in 2001, suggests that humans have a kind of hierarchy of learning, from remembering to understanding to applications to analysis to evaluations to creativity as sort of the highest of human thinking. And this seems like a very practical way of understanding designed learning using AR. Piaget's constructivism is also relevant, where learners are not passive receivers of information, but they have to actively engage in order to make sense or to sense make. So they have to learn by doing is the more sort of recent phrase. So learners have to be active agents. They have to be motivated. They have to care. They have to be respected as learners. They have to make decisions on their own learning and be supported in their endeavors. Vygotsky's and Bandura's social constructivism suggests that meaning is made socially and in groups. And so even as individuals feel like they are learning individually on their own, or that they've come up with something totally novel on their own, in most cases, they are in disciplines that were built up by the labor of many, many people and the insights and creativity and personalities of many. Kolb's experiential learning cycle also very much applies to this augmented reality experiential learning. Here, the human being is engaging in concrete learning in physical and AR space. They engage in reflective observation. They think of abstract conceptualizations from their reflections and express their ideas, and then they can go take their hypotheses into the world and actively experiment, right? So it's a continuous cycle of learning. Hutchins' distributed cognition also is relevant. This basic idea is that knowledge and memory can be stored external to the learner so that their working memory doesn't have to be overloaded in trying to remember all the knowledge and all the memory in order to engage in augmented reality space or in a learning space. So a properly designed object has to look a certain way, behave a certain way, interact a certain way to help humans understand the knowledge in that object in a learning context. Mayer and Moreno's multimedia learning theory suggests that properly designed learning objects will minimize extraneous cognitive load so that learners can use their working memory on intrinsic and germane cognitive load. So they have more mental energy and resources to apply to the learning. So that's those are the ideas that I think are relevant and hopefully helpful and practical. Um, so section break, how AR is generally designed. So Heather Dunaway Smith of Adobe Inc. Has set up an eight item sequence for setting up augmented reality using Arrow app. So she begins perfectly, I think, with goal setting. So in AR context and ambition of the makers will inform the design and the development and the deployment. So what follows would be sketching and storyboarding, perhaps scripting. Then prototypes are created. The assets are created. The AR scene is laid out or composited. Then there are interactions and animations that may be applied to the various objects and or to the scene. Those various elements are all tested. Every functionality that has been designed in has to be tested. And then there has to be sharing and publishing out for others to appreciate and to benefit the larger community. This 8-step sequence is not linear. It can be recursive, clearly. but it's super helpful, I think, in understanding process. This next slide shows an anteater inside the Arrow app building space. There are trees that can be seen. The shadows are below the objects, so the light is coming from above. And there are polygons representing the various shapes. The polygons are fairly large, which gives you an indication of just how small these objects have to be to function with motion, with behaviors, and so on in an AR scenario. Um, we're not talking 3D objects with millions of polygons. Let's put it that way. So context is important. If an AR experience uh, draws from the physical world, it helps to set the context accurately for where the visuals will spawn, where the sounds will spawn, the interactivity, the behaviors, and so forth. And in general, the digital elements of an AR display are in the foreground and the physical space is in the background. Although that doesn't necessarily have to be, you could also have digital elements right at the physical space, like standing on a physical rock or something like that. So in designing an AR scene, the human attention has to be guided. So the size of an object says something about its relevance, and the larger something is, the more attention it draws. The color brightness also draws attention uh, versus less bright or dimmer colors. Warm colors are more attractive than cool ones, and so on. Positive space draws human attention, whereas negative space or empty space or white space does not as much. Motion or movement changes over time. They draw the human eyes and attention. And audio can also be used to direct human attention, such as focusing on direction, the source of a sound, the change of a context, that sort of a thing. There are visual hierarchies that have to be designed to point attention to areas of visual interest. The visual elements should not compete among themselves, but work together towards a certain end. And based on the need for simplicity and sparsity, based on how augmented reality works, uh, those should require some pretty strict editing down. So lightweight files are needed for multiple reasons. One is that human attention towards transient multimedia is very limited. So if people are watching something, hearing something, if they're touching, smelling, tasting, they are perhaps limited in how much they can take in and notice. Their ability to see small details goes away for most people, even those with actually special training. The screen real estate is small on mobile devices, so AR has to work within those constraints if they are for mobile devices. And there are, so the files for AR have to be optimized with low file size, low polygon count, low frame rates, small sound files, and so on, in order to convey dynamic information, via the given devices today. AR is an active medium, so it shouldn't be designed for passive consumption. It should be interactive, social, and engaging. Section break, striving for accessible AR. So the areas we talked about for accessibility are now being readdressed here in more detail. So in terms of visual presentation and communications, there should be adjustments for low resolution in outdoors AR. There should be sufficient color values, darkness and brightness, and contrasts for a wide range of viewability. Color itself should not be used as a single channel to convey information by offering, so there should be offered multi-channel information. Digital and physical objects should not occlude uh, other objects. This is for perception, but it's also for safety. The scene orientation should be set up coherently for a person entering the augmented reality scene, as well as for them leaving the augmented reality scene. And if an AR visual should be experienceable from various angles, they should be tested from all angles for perception. So if there is sound, there is visuals, and text, all of that should be tested. Anything that should be perceivable should be tested. People should not be rushed as they go into an AR scene because they need sufficient time to perceive and consider the visuals, the motions, the sounds, the changes over time, and other aspects. Further, it may be helpful to use familiar layouts and positions of objects to lighten cognitive loads so that there can be understandings. So designers of AR need to understand the visual conventions on 2D and 3D and 4D, including how these visual conventions express in different cultures. When labeling various objects in different languages, for example, or for other learning purposes, the text, the symbols should be consistent throughout the AR scene. They should be fairly comprehensive. They should be visible and legible. And if there is sound or video, there should be text transcription uh, and including enriched transcription or more detailed transcription. Augmented reality in physical space has its own set of challenges. The physical spaces have to be safe for people to maneuver through, uh, no matter you know, their accessibility, such as through a wheelchair, through crutches, or other means. Um, there should not be anything occluding or covering learner vision uh, against any hazards. Um, people should not be asked to walk backwards or sideways. They should not be fatigued going through the AR experience, which might, if it's too excessive, for example, or too overly sensory. If they need directions to follow, they should receive those just in time, not have to memorize a long sequence of directions. And if there are wearables or tangibles or headsets, those should not be unwieldy or dangerous in their own right. In terms of interfaces and directions for navigation, it is important to address unclear or absent user interfaces. So people should be able to be oriented to where they are and what is expected of them when they enter the AR experience and when they exit. They should have an ability to re-experience sections or the whole. They should have clear directions for navigating sequences, processes, and movements, and they should be able to exit at any time. For example, if they are experiencing nausea or cybersickness, for example. Sensory and cognitive triggers should also be avoided. So if there are strobe effects, those should never ever be included in any visuals that you create, since those could lead to seizures, nausea, discomfort. You do not want to have motions that are uncontrollable. So those should be disabled or put into the control of users. Very speedy motions should be removed. Um, and if there are no user controls, perhaps that element may be removed. Uh, or if there's a lack of clarity on how to engage, that should also be considered. Anything that is too excessively busy, colorful, too action-oriented may cause challenges for the cognitive neurodivergent. So those should especially come with a warning, perhaps, and controls or a less excitatory version. Extraneous information may be left off if they may lead to extraneous cognitive load. Also, sensitive and controversial topics should be sensitively addressed. There should not be any messages that can be experienced as exclusionary or discriminatory. People should be included in the AR experience. Cybersickness refers to feelings of nausea and dizziness from some AR experiences. And there's been some recent research that has shown partly why this occurs. So the real world has high dimensional light data in the visual field, whereas the emulated AR one offers much less. There's flicker and there's contradictory timings, which can be problematic. There are also vulnerabilities based on demographic features of users, and all of that is important to take into account. In terms of the learning context, it would be important to have alternatives to the AR that enable the same depth of learning for those who would prefer not to do the AR or would prefer a different experience. For example, there can be notes that are offered for post-AR experience review and learning and practice. Perhaps there can be designed activities for post-AR experience review and learning and practice. Perhaps there can be pre-AR experiences, right? And so forth. So this next slide shows another view of the internal parts of Arrow with starter assets. Here, there's a fox looking at a body of water, and there's a giant rain cloud above. The text reads, and? So the prior slides shows some of the known challenges with deploying AR for learning. Shift left means addressing accessibility early in the design, development, deployment process to head off problems that might require excessive retrofitting. It is important to test and retest against potential harms prior to going live. It helps to have test users with a variety of different backgrounds and experiences to test the AR. This next slide is made from Deep Dream Generator, and it shows 3D flowers floating around in a circle. The references list follows next. This next slide shows a bicyclist speeding by a blur of trees. There's an implied motion. The aesthetics of this image is cartoonish a bit, and this was created with the Deep Dream generator. So the contact information for the presenter is available on slide 58. This is Shalin Haiju, 785-532-5262, SHALIN@ksu.edu. So if there are any questions, feel free to email. Thanks to the organizers of the Accessibility Summer Camp 2023 for including me. This is a pre-recorded session. Thank you for participating.